everybody, welcome to this video looking at differentiation and integration for functions represented as power series. So there are going to be two main motivations for this. One is that if we already have a power series representation of some function, then we can differentiate it or integrate it to get a power series representation for a different function, namely the derivative or the integral. And the other motivation is that if we want to do something difficult like differentiate or integrate a complicated function that's normally too hard to do, one thing we could do is represent that function instead as a power series, and then differentiate or integrate the power series. And it turns out that could be easier than differentiating or integrating the original function. Okay, so let's see how it works. And everything is dependent on knowing how to differentiate or integrate a power series. So let's suppose we have a power series with center A. So it's the sum of Cn times x minus a to the n. It has radius convergence R, which is bigger than 0, let's say. So remember, this means that this power series converges if we're in A minus R to A plus R. It diverges if x is bigger than a plus r or x is less than a minus r. Then what can we say? Okay, well, the function always is differentiable inside its interval of convergence, maybe except at the endpoints, but definitely in the interior. And there is a formula for how to differentiate the power series and integrate the power series. So if we want to differentiate the power series, well, there are two ways of looking at it. One is that we just interchange the derivative and the sum. The other way is that we just differentiate term by term. So what do I mean? If we interchange the derivative and the sum, that means we're summing the derivative of Cn times x minus a to the n. Cn is a multiplicative constant, we pull it out. So all we have to do is differentiate x minus a to the n. For that, we can use the power series, the power rule. We get n x minus a to the power of n minus 1, which is exactly what we have over on the right-hand side. Okay, so just to summarize, if we want to differentiate a power series, all we have to do is differentiate each term separately. So we differentiate Cn x minus a to the n. We get Cn times n x minus a to the n minus 1. So it's about as easy as you could hope for. One extra thing that changed: on the left, we had starting at n equals 0. On the right, we were starting at n equals 1. If you were to start on the right with n equals 0, then you would see here your first term would be a 0. So it wouldn't really change too much, but there's no point writing it. Also, if you think about what the sum on the left was before we started differentiating, the first term was C0 x minus a to the 0. So the first term was C0, just a constant. And if we differentiate that constant, it's going to go to 0. So that's why we change from n equals 0 to n equals 1. Okay, and then the same thing for integrating. If we want to integrate a power series, all we have to do is integrate term by term. So that means we have to integrate Cn times x minus a to the n. Cn is a multiplicative constant, we just pull it out. So we just have to integrate x minus a to the n. And again, it's the power rule. We get x minus a to the n plus 1 divided by n plus 1. Since it's an indefinite integral, we want to also add the plus c here. But here, both power series are starting with n equals 0. So no constants we don't drop any constants when we integrate. Okay, also, so you'll notice on the right, we have new power series for the derivative and the integral. They're not the same as the original power series, but their radius of convergence is the same. Maybe the interval of convergence is slightly different depending on what happens at the endpoints. So, the original power series might have converged at the endpoints, and then afterwards it might diverge at the endpoints. It just depends on the example. But the radius of convergence always will stay the same. Okay, so let's see how we can use this to find representations for other functions or to accomplish other tasks that we might want to do in calculus. So let's start off by finding a representation for arctan x as a power series. So right now, the only real starting place we have is with 1 over 1 minus x. So later we're going to see how to do it more systematically. But right now we want to start with 1 over 1 minus x as the sum of x to the n, and somehow chart a path to get to arctan x. And we can do this in 2 steps. So the first step is going to be to replace x by negative x squared to get a representation for 1 over 1 plus x squared. And then we're going to integrate both sides. That will give us a representation for arctan x, because arctan x is the integral of 1 over 1 plus x squared. Okay, so let's do that. We replace all the x's by negative x squared. We get 1 over 1 plus x squared is the sum of negative x squared all to the n. If we simplify, that's negative 1 to the n times x to the 2n. And then we integrate both sides. On the left, we get arctan x, which is the integral of 1 over 1 plus x squared. On the right, we just have to integrate term by term. So we have the sum of negative 1 to the n. We integrate x to the 2n, we get x to the 2n divided by 2n plus 1. And then since we're doing indefinite integrals or finding antiderivatives, which is the same thing, we have to add this plus c. So we have a plus c, a constant. And now if we want to find the plus c, one thing we could do is sub in an x value where we can compute the left and the right and try to solve for c. So for instance, let's sub in x equals 0. On the left, we're going to get arctan of 0. On the right, every term in the sum is going to be equal to 0 because, for instance, it starts with x and then it has x cubed and so on. So all the terms are going to be 0. So we get arctan 0 equals 0 plus c. solving gives c equals 0 because arctan of 0 equals 0. Okay, so now that we found c, we have our representation for arctan x. It's the sum of -1 to the n times x to the 2n plus 1 divided by 2n plus 1. And if we track the range of x, this is true for absolute value x less than 1. Okay, so we see here we can find power series representations for other types of functions. We just have to imagine how we're going to get from 1 over 1 minus x to the function we're interested in using algebra techniques, so maybe replacing x by something else or using all the techniques we saw in the previous video, and then either differentiating or integrating as many times as we like. Sometimes more than once, but in this case, just integrating once. Okay, so now let's look at the other motivation, which was tasks that we can't normally do using differentiation or integration. How can we accomplish them using power series? So for instance, let's try to do the integral from 0 to 0.5 of 1 over 1 plus x to the 7. And let's try to approximate this to within 10 to the minus 7 using power series. So normally this will be a very hard task because there is no nice antiderivative of 1 over 1 plus x to the 7. It's just not something that's easy. You know, if it was 1 over 1 plus x, it would just be ln of 1 plus x. It would be an easy u sub. If it was 1 over 1 plus x squared, it would be arctan x. 1 over 1 plus x to the 7 is not easy at all. So how can we do it? Well, at least one thing we could do is to first find a power series representation for 1 over 1 plus x to the 7, and then integrate that instead, which is going to be equivalent. So starting with 1 over 1 minus x, if we replace all the x's by negative x to the 7, we get 1 over 1 plus x to the 7, right? Negative, negative gives plus. X goes to x to the 7, we get 1 over 1 plus x to the 7. And since we're replacing x by x to the minus x to the 7 everywhere, that means we're going to have the sum of negative x to the 7 all to the power of n. So that's going to be negative 1 to the n times x to the 7n. And tracking where this is true for absolute value of negative x to the 7 less than 1, which simplifies to absolute value x less than 1. So now we have our power series representation for the inside. We can go ahead and integrate it. Remember, doing this integral meant find the antiderivative and then plug in the endpoints and subtract them. So those are going to be the same steps we follow. But rather than finding the antiderivative or finding the integral for 1 over 1 plus x to the 7, we use this power series representation instead. And all we have to do is integrate term by term. So if we want to integrate this sum, we have the sum of negative 1 to the n times x to the 7n plus 1 divided by 7n plus 1. So that's exactly what we did over here. So here is our antiderivative. We still have to plug in the endpoints and subtract them. But notice, finding the antiderivative of 1 over 1 plus x to the 7 is not easy at all. But finding the antiderivative of the power series is very easy because all we have to do is integrate the x to the 7n, integrate each term separately. These are way easier to integrate. Okay, so now that we've done the integration, we plug in 0.5, we plug in 0. And since this starts with an x to the 1 and then x to the 8 and so on, if we plug in 0, all of the terms are going to be 0. There is no constant term that starts. So all we have to do is plug in 0.5, the other term would be 0. We plug in 0.5, we have the sum of negative 1 to the n, 0.5 to the 7n plus 1 divided by 7n plus 1. And this is an exact answer for the integral, right, as a series, but it doesn't get, it doesn't really tell us what we were aiming for. It doesn't really tell us the value because it's kind of hard to look at this series and see what kind of value it is. So we need to approximate this to within 10 to the minus 7. This was our original task, to approximate this integral to within 10 to the minus 7. And now it's become a task for approximating this series to within 10 to the minus 7. But fortunately, this is something we know how to do because we've already studied how to approximate series. So now let's go ahead and do that, and we can basically forget where this series came from. So we have to approximate our series to within 10 to the minus 7. And it's an alternating series because we have this negative 1 to the n times a positive part. So we're going to use, as you would guess, the alternating series remainder test. There are two ways to look at that. So that we were saying if we add n terms, then the error is at most the positive part of the n plus first. Or if the nth term is small enough, then we just have to add the previous terms. So always we have to translate forwards or backwards by 1. So let's start by looking for which term is smaller than 10 to the minus 7. So you could start with n equals 0, n equals 1, n equals 2, and so on. I doubted that n equals 0 and n equals 1 will be small enough, so I went ahead and started with n equals 2. If n equals 2, the positive part is going to be 0.5 to the power of 15 divided by 15. And this is roughly 0.0000020345. And this is too big. So if you count the number of zeros and see where this appears, we have 5 zeros, and then there is a 2 in the 6th place. Okay, this is too big an error to predict the sum to within 10 to the minus 7. So we go to the next term when n equals 3, 7n plus 1 is going to be 22. So we have 0.5 to the power of 22 divided by 22. Okay, it's 1 point something times 10 to the minus 8. So in particular, this is less than 10 to the minus 7. So this term is going to be small enough. So we said that the third term, the positive part of the third term is small enough, smaller than 10 to the minus 7. And now we have to translate back by 1. So if the n equals 3 term is small enough, we have to add all the preceding terms. So we have to add the n equals 0 term, the n equals 1 term, and the n equals 2 term to get our estimate. So let's go ahead and do that. So the integral, which is the same thing as the sum, we just have to add the n equals 0 term and the n equals 1 term and the n equals 2 term, which are these three terms. And then you could go ahead and plug these in a calculator or in Google or something like that. And here is the answer it will spit out. So this integral is roughly 0.49951375325 with error less than 10 to the minus 7. Okay, and this is a pretty good information. Okay, we might not have an exact answer in terms of logarithms and exponentials and polynomials and everything and square roots. It might not be an exact answer, but with error less than 10 to the minus 7, it's probably going to be pretty good for every application that you might have in mind. So while we didn't get an exact value for this integral, it's almost as good. And we really needed power series to do this. This was not something where we could just figure out the antiderivative and plug everything in exactly. We really needed power series and then to integrate the power series instead. So this is kind of hopefully one motivation for, even though power series can seem kind of abstract, they're also kind of a box where you can also get things that are genuinely useful out of them. So they are worth studying also for applications. Okay, thanks everyone. See you next time.